Myself Prayak Patel, working as assistant professor in IT/ICT department of LG Institute of Engineering and Technology. Now in today's video lecture, I will discuss about the articulation point and strongly connected components. Now first consider the outline of the today's video lecture. First is articulation point and second one is strongly connected component. Now discuss the one by one point. First consider the articulation point. So first understand what is the articulation point. An articulation point in a connected graph is a vertex that if deleted then they disconnect the graph. Means we can say that if any node or vertex deleted from this graph, then this graph divided into two subgraph is called the articulation point. Consider the second point as in a connected network, single point whose failure would split the network into the two or more disconnected components is called the articulation point. For example, consider this graph. In this graph, consider the node number 2 as an articulation point, because here if we remove the node 2, then graph divided into two parts. First one is 1 and 4 and second one is 3 and 5. Also consider the node number 3 as an articulation point in this graph. See here, if we remove the 3, then 1, 2, 4 as a first part and 5 as the second part. Now here consider node 2 and node 3 consider as a articulation point. Now consider the another figure for the articulation point. In the second figure, consider the node number 3 as an articulation point. If we remove the node 3, then graph divided into three different parts. So consider this point as an articulation point. Now consider the next as how we can find the articulation point. In DFS tree, check the following condition for find the articulation point. Now first condition is U is root of DFS tree and it has at least two children. Then we can say that U as an articulation point. But if only one child of the root node, then consider this child or this root node not considered as an articulation point. So simply we can say that if the root node have two or more than two child, then consider this node as an articulation point. Now consider the second point. A leaf node of DFS tree is not an articulation point. Means leaf node not anytime as an articulation point. Now consider the third point. U is not root of DFS tree and not considered as a leaf node. Means we can say that the U as an intermediate node. Then it has a child B such that no vertex in subtree rooted with B. Means consider U as your node, V consider as a child of U, then V consider as a root node and subchild of the node V has a back edge to one of the ancestor of the DFS tree of your node U. So it's called the articulation point. Now understanding this or find the articulation point, consider the one equation. Using this equation you can find the low value. Here two values are used in the example of the articulation point. First one is DFN and second one is low. Now first, what is the DFN? DFN means in DFS tree we move from one node to another. Means consider the DFS sequence, depth first search sequence, consider as a DFN, means DFN number. And what is the value of low? Value of low find according to this equation. So for each and every node you want to find the DFN number and low value. So how we can find the value of low? Low of U equal to minimum of DFN of U, then minimum of low of W, and third part is minimum of DFN of W. So here what is the meaning of second part? Here first part is DFN of U. DFN of U means depth first number of U. Then second part is minimum of low of W. Here what is the meaning of W? W is a child of U. If you want to find the low for U node, then consider the child of the node U as a W. And in third part, what is the meaning of W? Here meaning of the W as a UW is a back edge. So consider the U as your node and W as a connected back edge with the your node U. So consider this equation for find the low of any particular data. Now consider the next step as a vertex U is an articulation point if W is child of U such that low of W is greater or equal to dfn of U. Means after find the value of low and value of dfn, you compare this value of low with value of dfn according to this equation. In this equation, consider U as your vertex or your node and W consider as a child of your node U. So here for the U as your node and W as your child, compare the condition low of W greater or equal to dfn of U. Now consider one example. Here in this example, find the articulation point for the given graph. Here in a given graph, there are total 6 nodes, node 0, 1, 2, 3, 4 and 5. Now consider this graph, and according to this graph you want to find the articulation point. Now first step of the articulation point example. Here consider the first step as a consider or define the DFS tree. Here for this graph, consider the DFS tree. In DFS tree you can consider any node as a starting point. So here for example, consider the node number 0 as your starting point for the DFS. So consider the 0 as your starting point. Then 0 to movement of the next node, consider as a, if you want to move from 0 to 1, then consider the first path from 0 to 1 here. Now consider the next node. 1 to 2 paths are possible, 2 and 3. Out of these two, select any one path. So here consider the path 1 to 2 is selected. Then after 2 to 3 and 4, both are possible, but we select any one. So here consider the 2 to 3. Next one is 3 to 4. So here consider the 0 to 4 path are there. Now after the position of the 4th node, here no any remaining node from the 4th to connected node. So you can backtrack on 3, then backtrack on 2, then backtrack on 1, then backtrack on 0. After the 0, consider the next path as a 0 to 5. So consider this is as a DFS tree. So in DFS tree, we cover each and every node. Now consider the back edge also in this tree. Here consider 3 to 1 path is not connected in DFS tree, but in graph there are one path is available from 1 to 3 or 3 to 1. So consider 3 to 1 as a back edge. Now consider the 4 to 2 path is available in a graph but not in a tree. So represent the 4 to 2 as a back edge in this DFS tree. Now consider the next step, step number 2. In first step we consider the graph and define the DFS tree using tree edge and back edge. Now consider the assign of DFN number. How we can assign the DFN number? We can simply say that according to your DFS sequence, or you visit the node in DFS, you can assign the DFN number. So here consider the first you visit the node 0. So here consider the node 0 as a DFN number 1. DFN number start from the 1. So here consider the root node as a 0, initial node as a 0. So DFN number of the node 0 equal to 1. In each and every node we represent the two number. First one is DFN and second one is low. So from the root, here consider the left side of the root represent the DFN number and right side of the node consider as a low number. So here consider for the node 0, 1 as a DFN number. Now consider the next node. We can consider the next node as a node number 1 because we visit the node 1 after the node 0. So here DFN number for node 1 equal to 2. Simply we can increment by 1. Now consider the next node as a node 2 and consider the DFN number for the node 2 equal to 3. Now consider the next node as a node number 3 and DFN number for the node number 3 equal to 4. Now consider the next node as a node number 4 and DFN number for the node 4 equal to 5. Sequentially we assign one by one increment operation. Now consider the after the 4th node we visit the node number 5. So consider the node number 5 as a DFN number equal to 6. So here we assign for each and every node one number and this number consider as a DFN number. Now consider the next step. In next step, step number 3, find the low, because in our previous condition we checked low and DFN, compare of these two elements. So first we find the DFN, then next find the low. How we can find the value of low and where we put the value of low? At the right side of the node, you can consider the value as a low. Now here consider the equation for the find the value of low. Your equation is low of u equal to minimum of DFN of u, minimum of low of w, and minimum of DFN of w. So here first part consider as a DFN of u, means your node consider as a u. So your node's DFN number as a first part. Second part consider as a low of w, and here w means child of u. So here consider, for example, for node 0, then consider the child of node 0 as a your child node 5 or node 1. Next consider third part DFN of w. Here DFN of w means back is from u to w. So here consider one by one node. Now here first we consider for which node you can find the low and in which sequence you can find the value of low. So from the bottom level, or you can say that the leaf node consider first or find the low of the leaf node first. So here consider the leaf node as a node number 4. So first find the low for the node number 4. So for node 4, low of 4 equal to minimum of DFN of u, means DFN of 4, your node's DFN. So DFN of 4. Second part is child of node number 4. So here in 3, child of node 4 is not available. So consider the second part as a dash or blank. Now third part is back is from 4 to 2. So here consider the back is from u to w. So here consider back is from 4 to 2. So consider the DFN of 2. Now here consider value as a minimum of 5, blank, 3. So here out of these 3, consider the 3 as a minimum. So final answer is 3 for the node number 4. So here consider for node number 4, low value equal to 3. Now consider the next node. Which node consider as a leaf node after the 4? Node number 6. So here consider the node number 6. In node number 6 consider the minimum of DFN of 6. Then child is not available. Then blank. Then back is it not available at the node 5. So here consider the for the node 5 DFN number equal to 6, but consider the node number as a 5 here. So low of 5 consider as a minimum of 6, dash. So here consider the minimum equal to 6 for the node number 5, low value equal to 6, and put the value 6 at this location. Now consider the next node. Here consider the next node as a from bottom to top level. So here already we find the value for node 4 and value for node 5. After that consider the node number 3 from bottom. So here consider the for node number 3, low of 3 equal to minimum of DFN of 3, minimum of low of 4, because here 4 is a child of 3, and third is minimum of DFN of 1, because 1 is a backcase from the node 3. So out of these 3 consider minimum of, here first DFN of 3 equal to 4, then low of 4 equal to 3, and DFN of 1 equal to 2. So minimum of 4, 3 and 2. Consider 2 as a minimum. So put the value 2 at location 3. So here we can say that node number 3 has low value 2. Now consider the next node as a node number 2. In node number 2, same process or same equation, means minimum of DFN of 2, minimum of low of 3, and minimum of DFN of 4, because 3 is a child of 2 and 4 consider as a backcase connected with it. So here consider minimum of 3, 2 and 5, and minimum consider as a 2. So put the value 2 in location 2 or low value of the node number 2. Now consider the next consider as a node number 1. In node number 1, find the value of low of 1. Here low of 1 equal to minimum of DFN of 1, minimum of low of 2, because 2 is a child of 1, and minimum of DFN of 3, because 3 connected with the node number 1 with the back edge. So here consider the value of these 3 as a minimum of 2, 2 and 4. So out of these 3, 2 consider as a minimum and put the value 2 in node number 1. Now last node. Which node is remaining? Node number 0. For the node number 0, same process are there. So here consider the for node number 0. For node 0, consider low of 0 equal to minimum of dfn of 0, minimum of low of 5, and second low of 1. In this case, consider the two child node. So here consider minimum of low of 5 and low of 1. And third part is back edge, and here back edge is not available. So consider only two part. Now consider the value of here minimum of 1 comma minimum of 6 2, and third part is blank. So here consider the minimum out of these two, consider as a 1. So consider answer for the low of 1 equal to 1. So consider this tree as a final tree for the articulation point example. In this tree, left side consider the DFN number, means in white color consider the DFN number. In yellow color consider the right side of your particular node as a low number. Now find the articulation point for this graph. Here consider the vertex U is an articulation point if W is a child of U such that consider the condition as a low of W greater or equal to DFN of U. Here consider U as your node and W as a child of your node U. So here consider one by one node. Now first consider the node number 5 and node number 4, because node number 5 and node number 4 consider as a leaf node. In our step we first write the, here consider for the leaf node is not any time considered as an articulation point. So here consider node number 5 and node number 4 are not an articulation point because these two nodes consider as a leaf node. Now for check the remaining node. So for remaining node consider the node number 0, 1, 2 and 3. Here consider the one by one node. Now first we consider the node number 0. For the node number 0 we can say that the node number 0 consider as a root node. And for the root node, one condition is that if the root node having a more than one child, means two child or more than two child, then this node consider as a articulation point. So here consider the for node number 0. Node number 0 is a root node of DFS tree and it has two children. So consider the node number 0 is an articulation point. So your first articulation point is node number 0. Now after that consider the node number 1, 2 and 3 one by one. First consider the node number 1. For the node number 1 we can say that for node number 1 we check condition low of W greater or equal to DFN of U. Here what is the W and what is the U? W means child of your node and U means your node. So here consider the node number 1 child equal to node number 2. So low of the 2 greater or equal to DFN of 1. So here consider the value of low of 2 equal to 2. So 2 greater or equal to 2. Yes, condition is satisfied. Then we can say that node number 1 is an articulation point. Now check for the next node, means for the node number 2. Here consider the node number 2. For node number 2 consider child of the node number 2 equal to node number 3. So low of 3 greater or equal to DFN of 2. So here consider low of 3 means value as a 2 greater or equal to 3. Condition is not satisfied. So we can say that node number 2 not considered as an articulation point. Now consider for the next node, means node number 3. For each and every node you check this condition without any process. Here we can consider the next step as a node number 3. Here consider low of 4 greater or equal to DFN of 3 because child of the node 3 consider as a node number 4. So here consider value of this 2 as a 3 greater or equal to 4. No. So we can say that node number 3 is not an articulation point. So finally we can say that node number 0 and node number 1 consider as an articulation point. So our final answer for the articulation point is node number 0 and node number 1 are an articulation point using this example. So here consider this as a articulation point example. Now understand the bi-connected components. What is the bi-connected components? Here bi-connected components means after removing the articulation point, remaining part considered as a bi-connected components, means different two graph considered as a bi-connected component. So here in this graph, here we can say that node number 5 as a 1 biconnected components and node number 2, 3 and 4 consider as a second biconnected components. Means in biconnected components there are no any articulation point is present, is called the biconnected components. So here consider the next topic as a strongly connected components. Now what is the strongly connected components? A directed graph is called the strongly connected if for every pair of vertices u and v there is a path from u to v and a path from v to u. So we can say that in this figure, for example, here consider the path from u to v and also path available from v to u. Means here consider from 0 to 1, then 1 to 2, then 2 to 3, then 3 to 0. 0 to 0, one cycle is available. So consider this is as a one strongly connected component. 2 to 4 and 4 to 2 path available. Means from u node to v node and v node to u node path is available. Then we can say that this is a strongly connected component. So here consider the algorithm or steps for the strongly connected component. Algorithm to compute the strongly connected components for a given graph. Now step number 1. Call the DFS for the graph G to compute the finishing time of each vertex. So here consider first step is apply the depth first search algorithm for your given graph G. Okay, and find the finishing time. Now consider the step number 2. Step number 2 is compute GT. Here what is the meaning of GT? Transpose of your graph G is called the GT. Means after performing the DFS operation on a given graph, transfer the graph into G graph into GT. Means we can say that we change the each and every direction of vertices of a given graph is called the GT. Now step number 3, call the DFS for the graph GT, but in the main loop of DFS, explore each vertex in decreasing order of finishing time. Means in first step, we consider the DFS, and in DFS we find the starting time and finishing time of each and every node. So according to finishing time of your node, consider the sequence or starting point for the second time applying the DFS algorithm. And step number 4, each tree in the forest computed in step number 3 is a strongly connected components. So here consider the final step as a strongly connected components. Now consider the step by step process. Step number 1 is call the DFS for the graph G to compute the finishing time for each vertex. So here consider this is a given graph. Now initially you can start your process from any node. For example, here we start the process from the node number A. So consider the node A as an initial node. So here consider A as a starting time and finishing time. So initially we apply the starting time. When process is stopped, then we apply the finishing time. So we consider A as a starting time equal to 1. Then A to B path is possible? Yes. Then we consider as a starting time 2. Then B to C path is possible. So consider C as a starting time equal to 3. Then C to F path is possible. So F starting time equal to 4. Now F to I path is possible. So consider here I and H, both node are here. So consider the H node. So F to H path is available. Yes. So consider the node number H as a starting time 5. Now H to I path is available. Yes. Then consider the I as a starting time 6. Now after that, when we reach the node number I, then I to any remaining node are not available or no any white or remaining node from the I. So here consider stop the process at node I, then color consider as a black for this node and assign the finishing time for the node number I. So finishing time of I equal to 7, then back to parent node means H, finishing time of H equal to 8, then consider the node F as a parent, then finishing time of the F equal to 9, then consider the node number C as a parent, then for the node C consider the 10 as a finishing time. Now consider the node number B as your parent node. Now from the B any node or any possible path is there. So here consider the B to E path is available. So not assign the finishing time to the node B. Here consider the path from B to E. So consider the last time equal to 10. So here starting time for the node E equal to 11. Now E to any path is possible? Yes, E to D. So consider the starting time of D equal to 12. Then E to G, starting time of G equal to 13. Now consider G node as a last node. From the node G, any remaining node are there? No. So here consider G as a last node. So assign the finishing time to G equal to 14. Then assign finishing time to D as a 15. Assign finishing time to E as a 16. Assign finishing time to B as a 17. And assign the finishing time to A as a 18. So here consider this is a final DFS sequence. So in this sequence, consider the starting time and finishing time, or assign the starting time and finishing time for each and every node. After that, step number 2. Here step number 2 means consider the or compute the GT. GT means simply we can say that in given graph direction is like is first figure, and in GT is after completion of first step we can apply the reverse direction or reverse edges for each and every edges. So here consider first edge is from A to B. So in second figure we can see that first edge from B to A, means you can change the direction of each and every edge. So here consider first edge from B to A. Then consider in first figure one edge from E to A. So in second figure we change this from A to E. So same way you can perform the GT operation, means change each and every vertices or each and every edge's direction. So here consider the direction for each and every edge is according to first figure to second figure conversion. Now consider the second figure for your next step after performing the compute GT operation. Now consider the step number 3. Step number 3 is call the DFS for the graph GT and explore your vertex in decreasing order of finishing time. So here consider the first figure as your first step and consider the second figure for your next step. So here consider initial point of the DFS algorithm. In DFS algorithm you can select any node as a starting node, but here we can consider finishing time or decreasing order of finishing time for the DFS sequence. So here consider maximum finishing time in this first figure is 18. So you can start the process from 18 finishing time, means from the node number A you can start your process. Means you can consider A as your starting time. Now A to any path is possible? Yes, A to E path is possible. In second figure you can perform the DFS operation on the second figure only. So here consider this for second figure, A to E path available. So starting time of E equal to 2. Then E to G path is available. So starting time of G equal to 3. Then G to D. So starting time of D equal to 4. Now from D to any path is not possible. So consider D as a finishing time and finishing time of D equal to 5. Then next consider parent node as a G. So finishing time of G equal to 6. Then consider the next as a node number E. Now for the node number E, node E consider as a parent node. From the E any other path is possible. Here consider E to B path is possible. So you can not assign the finishing time to the node E. You can perform the starting time for the node B. So starting time for the node B equal to 7. So here consider 7 as the starting time. From the B to any other path is possible? No. So we can assign the finishing time to node B. Then we can check for the node E because E is a parent of node B. So here for node E, no any remaining path or node is available. So here consider finishing time of E equal to 9. Now check for the parent node A. So here consider from A to any remaining path is there? No. So consider A as a finishing time equal to 10. Now after that some node are remaining. So for the remaining node, next time you consider as a maximum finishing time in figure 1. So here after that Remaining node consider as a H, I, F and C. Out of this 4 node, consider which node having the maximum finishing time in figure 1. So here consider the maximum finishing time as a node number C. So consider the node C as a starting node for the next time DFS or second DFS function. So from the C, consider the C as a starting node. So assign the starting value C11 or starting value equal to 11 in node C. Now C to any path is possible? No. So we can assign the finishing time to C as a 12. Now consider the next node. Now remaining node as a H, I and F. Out of these 3 nodes, consider which one having the highest finishing time in figure 1. So here in figure 1 we can say that 13 value consider as a next value, but here consider node number F as your highest finishing time equal to 9. So consider the starting node as a node F. So assign the starting time of node F equal to 13. F to I path is possible. So consider the I starting time equal to 14. I to H path is possible. So starting time for H equal to 15. Now from the H no any path is available. So consider finishing time of H equal to 16. Now assign finishing time to I equal to 17 and finishing time of F equal to 18. So here consider second figure as your final figure for the step number 3, in which we assign the DFN number, means here consider starting time and finishing time for the each and every node. Now consider the step number 4. In step number 4 we can consider as a or assign a tree or draw the tree for the given graph. Here in this graph we have a value according to your second DFS sequence. So here consider the one cycle. From the node number 1 we can move to the node number. Here consider first node as a node A, then consider node E, then E2 node consider as a G and B, and G2 consider node E. So this is considered as a first DFS tree. Now for second time we consider node C as another tree. Now for third sequence consider the F, then F to I, then I to H, in which sequence we move in this graph. So this 3 consider in second figure, consider the 3 part. 3 part consider as a 3 different tree, and collection of these 3 consider as a DFS forest, or consider the multiple tree of the DFS. So here consider these 3 as a DFS tree. Now consider the strongly connected components. In this sequence we can say that different tree consider as your strongly connected component. So your first tree is A, E, G, B and D. These 5 nodes consider as a first strongly connected component. So here we can say that in yellow shaded line, first strongly connected component as a these 5 nodes. Now second tree is C. So here consider yellow shaded line for the node C as the second strongly connected components, and last one is last 3 node. Here consider these 3 node consider as a strongly connected component. So in this given graph you have a 3 strongly connected component, first 5 node, then 1 node, then 3 node. So this is considered as a strongly connected component. So for find the strongly connected components, in today's video lecture I discuss about how to find the strongly connected components. For find the strongly connected components, first you compute the DFS for the given tree, then you can consider as a GT, means reverse or transpose of the given graph, and last one you can second time apply the DFS according to finishing time of your first sequence, and different tree consider as your strongly connected components. So thank you for watching this video.